Hey folks, in this video we'll review some of the basics of vector arithmetic. Much of this will seem familiar, but I wanted to extend it to 3 dimensions and really make a few things very explicit. So here are some of the goals for what you should be able to do after watching this video and reading the section in the book. So let's start with the definition. I want you to remember that a vector is a quantity with a magnitude and a direction. So we can draw these as arrows, either in 2D or in 3D. So we didn't do that on the worksheet. And there are 3 special unit vectors. On the worksheet we only saw 2. We talked about I and j that point in the x and the y directions, but we'll add to the mix k. So we call them unit vectors because they have a magnitude of 1. And so in the x direction, in the y direction, and the z direction, we have 1 for each of those, I, j, and k. Oh, and I forgot to mention, when we talk about vectors, they've got a magnitude, they've got a direction, but they don't have a position. So we can move a vector all around the plane without changing its name or changing the vector itself. Typically we draw them with their tail at the origin, but there are lots of good reasons why we might not need to do that, or we don't need to draw them on an axis at all. So I have an example for you. We can draw this vector on the xy plane, or let's call it the compass, the north and east plane. We know it's 30 degrees east of north, and it's got a length of 12. So if we decompose this in the I and j direction, or the x and y directions, we can draw a picture kind of like this. And really the tool we need is SOHCAHTOA. This is really one of the only things I can remember from my trigonometry class. So remember SOHCAHTOA, sine of an angle is the opposite over the hypotenuse, the cosine of the adjacent over the hypotenuse, and so on. So if this angle inside the right triangle is 60 degrees, we can say the sine of 60 is y over 12, the way I've drawn it, and the cosine of 60, x over 12. Then we can solve for x and y, and this is what we get. So once we're good with the ideas of the vectors I, j, and k, the unit vectors, and that we can decompose any vector in 2 dimensions or 3 dimensions using those, then we'll find the algebraic notation, or the bracket notation, can be a really concise way to write vectors. So let's review how we add or subtract vectors geometrically or algebraically. And geometrically, the idea is this tip to tail notion for addition. And algebraically, we do things component-wise. So we add the first components, the second components, the third components. Geometrically, we're stuck if we need more than 3 dimensions. Algebraically, I don't know, the notation might get a little cumbersome, but there's no reason we can't add together 2 17-dimensional vectors. Subtraction, we can negate the second vector and add it to the first. Or in the algebraic notation, component-wise, we can add subtract the first from the first, the second from the second, and so on. For scalar multiplication, when we say scalar, we just mean a real number. Geometrically, we can think of this as actually scaling the vector, stretching it or compressing it. And in algebraic notation, or from the algebraic viewpoint, scaling is done just by multiplying component-wise. So in this example, we just multiply each component by this scalar multiple, by this real number. Remember, a vector has a magnitude and a direction. The direction can be described using the coordinates or the components. We can also get the magnitude from that, so the length. Now, geometrically, the magnitude we find just by, I don't know, taking a ruler and measuring how long our vector is. But algebraically, we can use the Pythagorean theorem, which gives rise to the distance formula. And again, there's no reason we can't do this in more than 3 dimensions. This formula generalizes to as many as we need. So we can talk about a length in 12 dimensions, even if we can't imagine what that would look like. So here I have a, I don't know, let's call this a lemma for you. So what's the practical interpretation of this statement? Well, on the left-hand side of the equation, it's saying that the magnitude of the vector v when we multiply it by the scalar c is equal to, on the right side of the equation, the scalar c times the length of the vector. So what that's telling us is that if we measure a vector after scaling it, what we should find is that scalar times the length. Or in other words, multiplying by a scalar scales by exactly the same factor. Sort of how we described it anyway. But this shows that our geometric and algebraic intuitions agree here. So here's the steps we'll follow. We will write down the vector v in terms of its components. Let's call them a and b. And then the length of this vector on the left-hand side, c times ab, we can apply the definition of scalar multiplication to get the length of the vector ca, cb. And then we'll apply the magnitude formula to find the magnitude of that vector. We'll use some algebra, some of the principles of square roots, that they're multiplicative. And then what we get is we can factor out a c, and we see that this is exactly c times the magnitude of the vector ab, or in other words, c times the magnitude of v as we want it. So QED. One more example. Let's find a vector that points 15 degrees north of east and has a magnitude of 32. So I'll give you a shortcut that will turn out to be really, really useful. It's very easy to find a unit vector pointing in any direction we want. In particular, if we call the angle theta that it makes with the positive x-axis, so as theta gets bigger, we move in the counterclockwise direction away from the x-axis, then the vector cosine theta sine theta always has magnitude of 1. You should check this using the magnitude formula. And it points in the direction we want. So in this instance, a vector that points in the direction that we want is cosine of 15 degrees, sine of 15 degrees. It's not long enough. This only has length 1, and we want a vector with length 32. But this last claim that we just proved tells us we can scale it from 1 to 32 simply by multiplying by 32. So we'll do that, and we could write our answer this way, or if we want to give a decimal approximation, we can write it this way. All right, so tune in for the next video. You'll see a little bit about the dot product, and then in the video after that, a bit about the cross product. But good job.